Hello, in this video I will tell you about phase matching condition. Watch this video only if you already know what second harmonic is. If you don't know, the video about second harmonic generation will appear in top right corner. Let us consider, say, infrared light passing through a nonlinear crystal, which can generate second harmonic. It means that the crystalline lattice of this crystal has no inversion center. What happens as the light propagates through such crystal? Let us recall that nonlinear polarization can be presented as follows. One can imagine this as secondary sources, which arise as the light propagates through the crystal. At this point, we know nothing about these sources, such as whether they are in phase or not. This will significantly affect the total intensity of second harmonic which produced by these sources. Let us figure it out. As you may have already noticed, in the second harmonic process, the energy conservation law is fulfilled. The frequencies simply add up. Based on the following formula, which relates the k-vector to the frequency of light, we would also like to write the law of momentum conservation. But unfortunately, we cannot do it, because k-vector is also related to the refractive index of the structure. And the refractive index depends on frequency. Accordingly, the refractive index at frequency 2 omega is not equal to the refractive index on frequency omega, so we just simply cannot write this. And unfortunately, it makes the effective second harmonic generation more challenging. Let us introduce the following quantity, delta k, which is simply the difference between the k-vector on frequency 2 omega and on frequency omega. In Boyd's book, it's shown that based on Maxwell equations, we can write the following equation for individual frequency components En, relating them to the corresponding nonlinear polarization. Solving such an equation, we find that the intensity of second harmonic is proportional to the function sine x over x, which depends on delta k. The letter L denotes the propagation distance, so we observe the intensity at some particular distance. And at this distance, we would like to measure second harmonic. Let us fix some particular L and look at the dependence on delta k. We see at this plot then delta k equals 0, the second harmonic intensity is maximal. This is called phase matching condition. When the phase matching condition is fulfilled, this function simply equals 1, and the intensity will be proportional to the square of the distance that we have. It will simply grow quadratically. However, it cannot grow indefinitely because at some point the entire incident wave will simply convert into the second harmonic and there will be no more energy to generate it. In fact, this solution was obtained in undepleted pump wave approximation. If we take into account pump depletion, at short distances, the intensity function will still grow quadratically with distance, but at longer distances, it will saturate and be described by the square of hyperbolic tangents function. But if delta k is not equal to 0, which is actually what happens in real life, the intensity will not be described by any simple function. It will be expressed through elliptic integrals. However, the graph shown here demonstrates that the intensity of second harmonic will increase and then return to 0. This behavior is related to the fact that individual atoms of the medium are simply out of phase, and at some point the phases cancel each other out, causing the intensity drop to 0. But maybe there is still a way to achieve phase matching and neglect the effect of the dispersion? And indeed, there is a solution to this problem. We just need to consider the medium in which birefringence is possible. In such medium, two waves propagate, the ordinary and extraordinary wave, and their refractive indices are different. At the same time, for the ordinary wave, the refractive index does not depend on the direction. Its value is simply always equal to the radius of gray disk. And for the extraordinary wave, the refractive index will depend on the direction of propagation, but its value can be found graphically as the distance from the center of the green ellipse to the point where the line corresponding to the propagation direction intersects the ellipse. What happens when dispersion is taken into account? As the wavelength decreases, the refractive index increases. So for the birefringent medium, the refractive indices of both the ordinary and extraordinary waves will increase. However, it's turned out that there is a point where the refractive index of the ordinary wave at the fundamental frequency is simply equal to the refractive index of the extraordinary wave at the second harmonic frequency. This means that in a uniaxial medium, there are four directions where the phase matching condition is achieved. But we cannot always use this method, since not all media that generate the second harmonic are birefringent. For example, in gallium arsenide, we cannot achieve phase matching in this way, yet it is a very convenient material. Moreover, its nonlinear susceptibility is relatively high. What should we do in this case? Let's take a closer look at how the phases from individual atoms in the medium are combined. For instance, in the case of phase matching, all individual atoms emit in phase. The phases combine, and we get the maximum amplitude. But in the absence of phase matching, the phase shifts slightly each time, and the maxima alternate with minima when summed. Nevertheless, the light travels at a distance of p over delta k. The intensity, in the absence of phase matching, reaches a maximum and then falls again. What if we could reverse the phases of this part of the vectors, the left semicircle, so that the intensity would not fall into a minimum? It might look something like this. Then the intensity would gradually increase each time, even not as much as the phase match condition is fulfilled. And we can actually do this. We just need to create a medium where the corresponding component of chi susceptibility tensor would change sign after a distance of pi over delta k. So we need simply create a structure where the lattice direction periodically changes. And in this case, we achieve the condition of quasi-phase matching. Now you see that obtaining phase matching or quasi-phase matching is not so hard. Thank you for watching. Bye.